Swayam Prabha. Digital India. Educated India.
Alright, so let's look at implementation now. So, implementation basically means that we need to figure out a sort of efficient quantum circuit that will take us from this representation to this representation. Okay, so let's do that. So, we want to implement this map. Okay. So, what we will do is we will consider a special case first, okay, and we will consider a small instance of this problem. So, with small n equal to 4 and capital N equal to, what is capital N if small n is 4? Okay, great, you were listening. So, indeed, so let us consider this, and so we have our x as a sort of 4-bit register, 4-qubit register, and let us try to build the circuit slowly. Okay, so we will see it via an example, and then we will as an exercise you can generalize this to arbitrary n. Okay, that there is nothing to it, so it is not like I am giving you the harder thing to do. In fact, I never do that. Okay, good. So, let us look at x. We want to take this to this, right. So, what is this going to look like specialized for our setting? So, square root n is 1 over 4. Okay, and now let us compute the coefficients. Okay, so when we look at x equal to, so we have to sum over all gamma in Zn, right. So, let us look at the coefficient. So, for gamma which is 0 0 0 0, what is the coefficient? It will just be 1, right. So, it is omega to the 0. So, this is that. Then for 0 0 0 1, what should it be? Omega to the minus x, no. So, gamma here is 1, right. And then when gamma is 2, you will get this, okay, plus gamma to the minus 3x and so on. Okay. So, this is our this is what we want. We want to go from x to this. Okay, so the key observation that allows us to implement this circuit efficiently is that actually this quantum state that we ended up with is not entangled. So, you can actually write it as a tensor product of 4 different qubits. Okay, and when we write it as the tensor product of 4 different qubits, then we will see that actually it is there is an efficient way to go from the qubits in x to these qubits via some some reasonably simple circuits. So, let us look at that. Okay. So, as I said, the key observation is that the previous state that we saw is unentangled, right. So, you can write it as the tensor product of 4 qubits, let us call them psi 0, psi 1, psi 2 and psi 3, such that the above state is the tensor of these. Okay, and you can work out what are these psi I. So, I will write them here. Okay. So, 0 plus omega to the minus 8x1 over square root 2. This is the most significant bit. Tensor 0 plus omega to the minus 4x1 over square root 2. Okay. Tensor 0 plus omega to the minus 2x 1 over square root 2, tensor 0 plus omega to the minus x 1 over square root 2. So, you can open up these tensors and verify for yourselves that this is what is the state that we had. Okay, so now this is really nice. Okay, so I would like everyone to stare at this. So, first of all, notice that if for a moment I forget about these omegas here. So, this is some this is some 0 plus alpha I 1 over root 2. Okay, so this is these are my coefficients of 1. And these are following a very natural pattern, right. So, this is omega to the minus 2 to the I, right. So, 2 to the n, 2 to the n minus 1, so on and so forth, and in fact that is the generalization for the case of n as well. So, it is just so instead of 8 which is 2 to the 3, you will have 2 to the n. Okay. So, now actually it is 2 to the n minus 1, right. So, my n was 4, yeah. So, this is 2 to the n minus 1, not 2 to the n. Yeah. Okay. So, now I want to go from x, right, x0, x1, x2, x3 to psi 0, psi 1, psi 2, psi 3. This is what I want to do. I want to compute a circuit that will take x to this, right. This is what I would like to do. Now, some simplifications will help us out. So, note that this whatever is happening in the exponent, this is integer multiplication, right, mod n. So, now what is, here is my question. Okay. So, what is omega to the minus 8 x? What is this equal to? So, x is it is 2 summation 2 to the I xi, right, where I is going from 0 to n minus 1. I am just going from binary to integers, nothing more, right. So, I am just saying that I want to use the fact that x is this, together with the fact that omega to the 16 is 1, to simplify this. So, let me try to motivate where I am going with this. What I would like to do is, I would like to build a circuit. Okay. So, I have x0, x1, x2 and x3, right. This is my x, and I am trying to go to this tensor of size, correct. Now, the way that we have written it here entails all the bits of x for even a single bit of any of the psis, right. So, psi 0, psi 1, psi 2 and psi 3 all depend as written on the whole x. What I am trying to go towards is to remove the dependence on all the bits of x and only try to depend on fewer bits. So, for instance, for the MSB, I claim that I only need to worry about the least significant bit of x. So, what I am instead of going from x to the size that we stated, right, I am actually going to go to the I will map the least significant bit to the most significant bit of the output. Okay. So, let me call these as gamma 2, gamma 3, gamma 2. Actually, I should move them here, so I have more space. So, I want to map x 0 somehow to gamma 3. Okay. And my claim is that I can actually simplify this. So, I have omega to the minus 8x, right. So, I can write this as omega to the minus 8 summation 2 to the I xi, right. Now, do you see that 0 to 3, right. Now, do you see that it is only for I equal to 0 that I will get something that will survive. Basically, for I equal to 1, what is it? It is 2 times x1, 8 times 2 is 16. So, the whole thing dies, right. So, this is nothing but omega to the minus 8 x0. Okay, and this I claim can further be simplified to minus 1 to the x0. So, this just follows by the just open up omega. Okay. So, omega is e to the 2 pi I by n, right. Yeah, this is omega. So, what is omega to the 8? Wait, I made some mistake here. It is not by 8, it is by 16, right. That is what mistake I made. So, now what is omega to the 8? It is nothing but e to the 2 pi I. No, wait, pi I, good, yeah, good. So, it is e to the pi I, this is just minus 1, is not it. So, omega to the minus 8 x 0 is omega to the 8 to the minus x 0, which is minus 1 to the minus x 0. Does everyone agree? Does everyone agree? Okay, so good. So, basically now let's stay on the same board here. Okay, now let us see what we wanted. So, we have this 0 plus omega to let us focus our attention on this thing. Okay, so we want to go to this term here, which is what? It is 0 plus minus 1 to the x 0 1 over root 2. Does everyone agree? We want to go to this. So, we have already made some progress because our wire, at least we started it from x 0 and we ended it to this. So, we can see that all that you need for this gamma 3 is just x 0, you do not in fact need anything else. Okay, so, that is great. So, now what is what will take x0 to this? What transformation do you know that takes x0 to this quantity? It's just the Hadamard transform, right? It's exactly the Hadamard transform, and we have done this many times, so we will not do it again. So let's put this, let's put this Hadamard transform in. Okay, so what we do here is we simply apply the Hadamard transform here, and that gives us our most significant bit. Okay, now what about x1, or I am sorry, not what about x1, what about gamma 2? So now again let us go back to our second bit over here, right, the second most significant bit. So now we are looking at, so let us erase the orange from here and let us put it over here. So now we are looking at this. Okay. So one sort of thing to observe is that okay, so minus 4x can also be simplified. Okay, so instead of again doing it from scratch, I will just write this down. So it will follow exactly as we have seen before. So this is omega to the minus 4 x0 times it is actually minus 8 x1. Okay, so you can again just expand out x and you will get this. So now again this minus 8 x1 you can simplify, right. So it becomes minus 1 to the minus x1, okay, and omega to the minus 4 x0. Okay. So I want my second most significant bit to be this. It should be 0 plus minus 1 to the minus x1 omega to the minus 4 x0 1 over root 2. So now if I apply Hadamard, what will I get? So if I apply the Hadamard transform, okay, so suppose I apply the Hadamard, then what do I get? As before, I am going to get 0 plus minus 1 to the minus x1 1 over root 2. So I have made some progress here, but now what do I want? I want this additional phase shift to happen, right, and what is that phase shift? It is omega to the minus 4 x0. So if x0 is 0, then nothing should happen. If x0 is 1, then it should get omega to the minus 4 phase shift. Okay. So this can be implemented using a controlled phase shift gate. Okay. So this can be written down as a unitary operation. In the interest of time, I will not do it, you can refer to the notes, but basically we will represent this gate as omega to the minus 4. Okay, so you see that the input of this gate is x0. Okay, and this will give us the gamma 2 that we want. Okay, so for x2 and x3, let me just write it down. So again I have the h, okay, then I have the omega to the minus 4. This time the input is coming from x1, and then I also have omega to the minus 2 with the input coming now from x0. Okay, this will give me gamma 1. And for x3 I will get h, okay, omega to the minus 4 coming from here, okay, omega to the minus 2 coming from here, okay, and then omega to the minus 1, coming from here, and this will give me my gamma 0. So, I would like you to verify for yourselves the other bits. If you want, I can write them down in any case. Okay. So, yeah, so x1, as we already saw, goes to 1 over root 2 0 plus minus 1 to the x1 omega to the minus 4 x 0 1. We already, this one we did in complete detail. Okay. X2 and x3 I did not do in complete detail, I am just writing them down, you can verify for yourselves. So, this is going to be 0. Plus minus 1 to the x2 and then omega to the minus 4 x1 minus 2 x0 1. And x3 will go to these should be minuses. Yeah. Okay, so basically use controlled phase shift gate. For omega to the blah. Okay. So, you can see that this circuit is efficient, right. So, assuming that these controlled phase shift gates are efficiently implementable, which they are. We have not studied them in too much detail in this class, but maybe we will come to them again. In any case, you can check for yourselves that these are sort of efficient unitary transformations. So, this is the special case of small n equal to 4, and it generalizes very naturally to any n, right. And it shows that in fact, to implement this circuit you need only a quadratic number of gates, order n squared, where order small n squared. Okay. So, this is order poly log n. Okay. So, this log here is very, very important. Okay. So, classically this is more like poly, or I do not know, maybe actually it is not, it is more like this. So, this factor n here, right, this becomes a problem because this is 2 to the n, 2 to the small n. Okay. So, classically this computation would have taken us exponential time. Here we are doing it in polynomial time, the polynomial circuit size, and this is not by itself, I mean this is, as stated, once again not immediately useful, because I nevertheless need to measure finally to get some output, right. So, maybe that I can compute this QFT and it gives me some nice quantum state, I can compute it efficiently, but I still need to measure and get something useful out of it. So, Simon's algorithm over Zn, we are almost out of time. So, maybe this is a good place for us to stop the formal discussion. We will just end with a intuitive discussion about where this is headed. So, Simon's algorithm over Zn, what is it going to do? If I give you a periodic function, okay, so any function where f of x is equal to f of x plus s, right, or not only x plus s but x plus k times s for any k. So, basically it is a periodic function, okay, the function it is periodic. So, now what is Simon's algorithm over Zn going to do? It will do something very similar to what we were doing over Z2n, okay. So, what we will do is that once again we will prepare our input superposition by applying the Hadamard, okay, then we will apply our function to this, okay, and we will measure the function register. So, what this will do is that it will collapse the function output to one particular value. So, we think of these as many different colors, like so there is the input space, right. Think of the range of the function as many colors. So, because the function is periodic, it means all the points that are separated by this period all map to the same color, correct? Everyone gets it? So, now when we measure the second register, right, we are basically collapsing down to one color. So, now the input, I mean the input register will collapse to a superposition of points which are separated by this period, right. And now what will we do now? So, let us say I measured, I got some x0 which may be the first point for that color. Let us say the color whatever it is, color red, okay. So, I got let us say that f of x0 is red, and now I measured, so I got x0 plus ks for some k 5, x0 plus 5s I got. Now, my goal is to recover s. Now, what happens if I repeat? What you want to say is that let me now repeat it and recover s, right. Now, if I repeat this, do I recover s? Why? Because the second time I do this, I will get some completely different color when I measure my second register, right. So, then I will get y0 plus 20s. So, this has given me no information. So, what I will instead do is I will apply the quantum Fourier transform, and now think about why that should help me. When I apply the quantum Fourier transform, right, this issue that the colors might keep changing, this actually goes away. So, the quantum Fourier transform moves me to a space which is independent of the color. So, when I repeat it, I will get multiples of 1 over s, or more precisely capital N over s. Anyway, so we are out of time, let us stop here. So, but it was the right intuition in some sense, but it was, as I said, wrong in the, what I mean by that is that of course it does not work, but moreover, right, we are not paying attention to the essential difficulty, which is why we are applying the Fourier transform in the first place. So, that is really something worth thinking about, right. So, at this stage, if I have already collapsed to this input superposition for the same color, why can't I just do a few measurements and get something already? Why do I need to even apply this quantum Fourier transform, right? Let us stop here. Thank you.